Hello students, and welcome to our video covering topics in section 12.2 of your textbook. In this video, we will begin with a general overview of vectors. We'll talk about an algebraic and geometric interpretation for vectors. Then we will talk about how to work with vectors, adding them and scaling them. We will move on to a few special vectors that I want to point out, and then we will end with a discussion of how to represent vectors using points. All right, let's jump right on in. Let's do our vector overview. Any good overview begins with a definition? That's probably not true, but this one does. Okay, so a vector, by definition, this is a mathematician's definition, it is a quantity with both magnitude and direction. And if you have never seen a vector before, this probably makes no sense, but we will see it in context shortly. Before seeing it in context, I want to drop a little bit of notation on you. So in general, if we're going to write a general vector, we'll either write it with a bold-faced V or with a V with a little arrow over it. Both are widely used in mathematical notation. When I'm handwriting, I like to write a little arrow over it because it's easier than like trying to bold in handwriting. But if you're typing, definitely easier to smash that Control B than to figure out how to put an arrow over your B. Okay, so we'll use both. I think your book likes the bold-face V. Then also just the magnitude of a general vector. We would take the vector, say bold-face V, and put absolute value signs around it. Or because the absolute value signs are already used for absolute value, some textbooks like to have these like double bars around it. And I think your textbook likes the single bars, but you would see both in the wild. But okay, so let's now interpret vectors first geometrically. So in geometry, a vector is an arrow. So remember, a vector is a quantity with magnitude and direction. Well, we have an arrow that points in the direction, and the length of the arrow is the magnitude. So this is really what you should have in mind. Something like this. Okay, if you're in 2D, you've got a little arrow. It is pointing in a certain direction, so that's the direction of your vector, the direction it's pointing. And what is the magnitude of your vector? It is the length of this arrow. So often in physics, things like force or something will be a vector, and you represent the force pushing on an object. Well, you say, all right, well, the force is pushing in a certain direction with a certain magnitude, and then you would have the direction be, you would represent it with an arrow, and then a bigger force would be represented with a bigger arrow. And if you're in 3D, okay, and this is another possible representation of a vector. A little bit more terminology. This starting point here of your arrow, that's called the initial point, but because life is too short to continually type initial point, we're going to call it a tail. And similarly, the point where the vector ends, the tip of the vector, we're going to call that point to the tip, because once again, who's going to keep saying terminal point all term? Not me. Okay, so somewhat confusingly, mathematicians treat all vectors with the same length and direction as equivalent. So for example, all of these vectors right here, mathematicians would say, that's just the same vector, just in a different position. Similarly in 3D, all of these vectors, the exact same vector, just moved around. Why mathematicians do this? Well, it's useful. And we will see this. It's nice to be able to move vectors around. This is actually one thing that's kind of different from points. Points are things that just they're fixed. They're just somewhere. But vectors, it's nice to move them around. So this is one benefit of thinking about vectors, is that we get to do this. So yeah, it might be kind of weird to think about at first, but I believe it will become second nature to you soon, if it's not already. Okay, but if you're worried about vectors floating around all the time, we almost always draw the vector coming out of the origin, which is called the standard position. So in 2D, we would draw a vector there coming out of the origin, or in 3D, the vector, coming out of the origin looks like that. Okay, so that's vectors in geometry. Now let's talk about how they're represented algebraically. So in algebra terms, a vector is just a list of numbers. And in fact, this is what computers think vectors are. It's just a list of numbers. The computers don't think in terms of arrows. So, all right, I've got a general vector v. If it's in 2 dimensions, it might be, I would write it as these angle brackets, v1 and v2. And maybe if I was in 3 dimensions, it would be v with angle brackets, v1, v2, v3, where, okay, these are just numbers. So back in this case, this v1 and v2, these numbers are the coordinates of the tip of the vector if the tail is at the origin. So that's how we represent a vector with numbers. We say, all right, well, this vector, maybe it's living somewhere in far out in space, but when we represent it as a list of numbers, we say, all right, well, let's represent it by the numbers the tip would have, the coordinates the tip would have if the tail were at the origin. Same with this guy over here. So for example, if we're in 2D and we have the vector 2, 5, well, then that means that the coordinates 2, 5 will be the tip of the vector if it is oriented at the origin. And similarly in 3D, if we have a vector 1, 3, negative 1, this means if we go 1, 3, negative 1, that this, somewhere there is going to be the tip of the vector with its tail at the origin. Now that we have this algebraic way of thinking about vectors, we have a nice way to calculate the length of a vector, which is, again, its magnitude. I guess if we didn't have the algebra representation, we'd just be measuring the lengths of arrows. But all right, if we, in the list of numbers way, we use the Pythagorean theorem. So for example, if this is our vector 2, 5, then we're looking for the length of this vector. We notice, oh, well, I see a right triangle here with one leg of length 2, the other leg length 5. And so the length of this vector is, using the Pythagorean theorem, is the square root of 2 squared plus 5 squared, which happens to be square root of 41. If we're in 3 dimensions, then we've got this generalization of the Pythagorean theorem that we've seen with the distance formula, where it's like, okay, 1, 2, 3. The length of this resulting vector is the square root of 1 squared plus 3 squared plus minus 1 squared. So you take the components, square them, add them together, take the square root. And that gets you the length. And okay, if you wanted to do this in 17 dimensions, you certainly could. And it's certainly easier doing it algebraically than trying to draw a 17-dimensional vector and measure its length. Okay, let's talk about adding and scaling vectors, which I actually think is kind of interesting. So, all right, adding vectors. In the algebra sense, it's pretty straightforward. You just add the components. So for example, if you've got 2 vectors, we'll call them V with components v1, v2, v3, and W with components w1, w2, w3. Then adding the vector that you get when you add V plus W is a vector where the first component is just what you get when you add the first components of V and W. Second component, you add the second components. The third component, you add the third. So yes, V plus W is itself a vector, and the components are V1 plus W1, V2 plus W2, and V3 plus W3. And maybe that feels natural because maybe you think, I don't know how else I would add these things. This seems like a natural way if you're just kind of didn't even know why you wanted to add vectors. You might say, well, this is how I might do it. But what does this mean geometrically? Well, geometrically, this definition of adding vectors it corresponds to what is sometimes called tip-to-tail addition of vectors. So for example, suppose we have a vector v down here and a vector w here. Then adding w to v, what you might do geometrically is you take this vector w and you kind of slide it down until it comes off of the tip of v. And then the vector v plus w is the vector you get where this is the new tip of the vector. And this, I think, makes sense when thinking about times you might want to add vectors. Like maybe you're traveling and you say, all right, you're traveling in this direction for this length, and then you travel in this direction for this length. And how far did you travel, and in what direction did you end up? Well, all right, you traveled this far in this direction. And similarly with forces, when you want to add up forces, this physically turns out to be what you want it to be. This ends up being the resultant force. So yeah, and these two are equivalent. Tip to tail addition, if you work it out with components, you'll find out that the components of v plus w this way are indeed this. And last thing I want to say is that something that is true in the algebra sense is, or maybe clear in the algebra sense, is that v plus w is w plus v. They're the same. You can switch the order of v and w and all the components and nothing changes because addition is associative and, commutative. Commutative. There we go. And similarly here, like instead I could have added v to w and I would have ended up at the same point. And so w plus v, I get the same vector. Okay, so what about scaling vectors? Well, in algebra land, this means we scale each component. So for example, if we have some vector v and then some number c, then scaling v by c, we write as c multiplied by v. And you calculate that algebraically by just multiplying each component by c. And let's see what that's doing geometrically. So in geometry, scaling means you end up stretching, shrinking, or flipping along the line through your vector. So for example, all right, we've got this vector v, and suppose we want to multiply v by 2. So scaling v by 2. We would get this longer vector in the same line. It just now has double the length of our original vector. If we scaled our vector by -1, that actually flips the vector in the opposite direction. And you could see this by going back to the algebraic definition and say, oh, it's just, if c was -1, then our vector would go from v1, v2, v3 to minus v1, minus v2, minus v3. And maybe if you scaled by 1/2, then you would get a vector of length 1/2 v. But notice whenever you're scaling, you're just moving the tip of the vector along this line somehow. So scaling a vector doesn't change the direction at all. And now that we know about scaling, we can talk about an important concept called parallel vectors. So by definition, two vectors are parallel if, in the geometry sense, they're parallel if they point in the same direction. So, okay, all of these vectors, they are different lengths, but I'm going to say they point in the same direction. Even though, like, this guy's definitely pointing up to the left and this one's pointing down and to the right, we kind of say they're the same direction because they'll fall along the same line. Well, I don't know. Forgive me for this, but all right, this is what I'm going to say. I'm going to say they point in the same direction because they fall along the same line. Maybe a better way to have said it would be to have said that, okay, they're all, the lines through the vectors are all parallel, which then it would really make sense why I would call those vectors parallel. Okay, so do with that with what you will. The algebraic way of telling if two vectors are parallel is that one is a scalar multiple of the other. So here, I'd say vector v is parallel to vector w, and here these like two parallel bars is just, I don't know, lazy person's way of writing are parallel or is parallel to. So v is parallel to w if and only if v is equal to some number times w. And because this number can be negative, that's why I'm saying, well, they're like the same direction. Okay. Why do I keep bringing up a source subject? Okay. Oh, yeah. Just this is handy. This is handy. I'm just going to say it. We'll use this. And if you're taking this from this class from me, then I know this is going to be helpful on one of your homework problems. So, yeah, remember that. That's just a nice property to know that if they're parallel, one is a scalar multiple of the other. All right. Let's talk about a few special vectors. First, we're going to start with what's known as the standard unit vectors. So in physics, they give the standard unit vectors special names. So the standard unit vectors are this 1, 0, 0, 0, 1, 0, and 0, 0, 1, at least if you're in 3D. And this first one, physicists call I, or sometimes I hat. Here, this second one, they call J or J hat. And this third one, they would call K or K hat. So if you're in 3D, then this vector here, 1, 0, 0, that's I. This vector here is J, and this vector here is K. So this leads to actually a different possible notation for your vectors. So if you have, the standard mathematical notation of a vector in component form, v is v1, v2, v3, you can write this in kind of the physics way, where this is equal to scaling the vector I by v1, scaling the vector j by v2, and scaling the vector k by v3. And if you just did this by hand, you scaled these three vectors and then added them all up, you would certainly get this vector back. So you might see in some books a vector like 7, 0, minus 3 in the mathematical notation written like so. And your book does this too, because it's pretty standard, and the topics in this class are applied so widely that, yeah, you just got to be comfortable with both. One thing that can be kind of annoying is that, okay, something like 7i plus 0j minus 3k, this 0j will often just be ignored. And so it'll be like 7i minus 3k. In which case, if there was a 0 on the k, maybe you would be confused about what dimension you were in. Yeah, it's assumed you'll get it from context. Okay. Right. Before moving on, what is a unit vector exactly? Well, a unit vector is a vector with length 1. So these standard unit vectors, you could calculate them, definitely of length 1. And any vector whose length is 1, we would call a unit vector. All right, we've got a special vector called the 0 vector, and I just wanted to flag it and let you know you might see it as written as a just bold 0, or a 0 with a vector over it, or if you're in 2 dimensions, it's between angle bracket 0, 0, and 3 dimensions between angle bracket 0, 0, 0. And if you are drawing it, you would draw it as a point at the origin. So like that in 2D or like that in 3D. And yeah, we still consider this a vector, even though it doesn't have any direction or any magnitude. Yeah, okay, we'd say it has 0 magnitude, but don't ask me what direction it's in. Okay, so that's the 0 vector. We definitely want to be able to have a vector that is a 0 vector. And then the last thing I want to do is just talk about vectors from points. So suppose we have 2 points in the plane or in space, say P with P1, P2, P3 are its coordinates, and Q as Q1, Q2, Q3 with coordinates, then we might want to talk about the vector that, say, starts at P and goes to Q. So yeah, if we're given the initial point and terminal points, I said life was too short, and then I just did it anyway. But if we take the initial terminal points, uh, how do we find the standard representation of a vector as a list of numbers? Well, what you do is you just take the first component of q, subtract the first component of p, then take the second component of q, subtract the second component of p, third component of q minus the third component of p, and make those the components of your vector. And this just comes from the fact that, okay, well, if you're going from p to q, well, how far in the x direction do you go? Well, that's going to be q, where you end up in the x direction, q1, minus where you started in the x direction, p1. And similarly, like, oh, then how far in the y direction and how far in the z direction? So there you have it, folks. Just as a quick example, if you had the points p and q and you're going from p to q, order does matter. If you switch these up, you would actually get the arrow in the opposite direction, which, oof, that can mess up some calculations later in the term. So just make sure your arrow is pointing in the right direction when you do something like this. Okay, and so this would be 1 minus minus 1, and then second component minus 2 minus 3, and the third component is 5 minus 0. And you do this out, this is 2 minus 5, 5. Okay, thanks for playing. I'll see you in the next video.